One of the most iconic exoplanets is fictional, but could it exist? So our solar system contains a single star, the sun, obviously. But that's actually somewhat unusual because multiple stars are very common. And yes, there's a little bit of a weird language thing here where star can refer to the actual physical body of a single star, or it can refer to the system of stars together that form a star. So the binary star Sirius contains 2 stars. Is this a little confusing? Yes, I think so. So in this video, I'm only going to be using the word star to refer to the physical single body of a star, and I will use the term stellar system to refer to the grouping of stars as a whole. So with that in mind, any individual star actually has a 50% or more chance of being part of a multiple stellar system. And if you're anything like me, one of the first things that you might wonder when hearing that is, well, what about planets? So can multiple star systems have planets? And well, if you've seen my video on Proxima Centauri, you already know that the answer to this is yes, because Alpha Centauri is a triple star system and Proxima Centauri has its own solar system. Well, this has been fun. See you next time. I'm just kidding. Obviously, there's so much more we have to talk about. Like, the planets of Proxima Centauri are orbiting just a single star, but could you have a planet that's orbiting 2 stars at once? And just, I know what you're probably thinking because I think it is the most famous exoplanet, and I don't think I can show it here because I have no lawyers to defend me from Disney, but of course we're talking about Tatooine. Luckily, NASA pictures are public domain, so I can legally use this gorgeous picture to illustrate the concept. And if 2 stars just isn't exciting enough for you, can you have planets that are orbiting 3 stars at once? And if these kinds of systems are even possible, does that mean that they actually exist? This is fascinating stuff, so let's go. Let's start by considering basically the simplest scenario, which is the stability of planets orbiting in a binary system with 2 stars. There are 2 basic types of planetary orbits you could identify here. So a planet could be orbiting just one of the stars of the binary, or it could be orbiting both of the stars of the binary. And these are called S-type and P-type orbits, respectively. I think that S-type and P-type stand for satellite type and planetary type, but I'm not positive about that because literally nobody ever says that. It's just S-type and P-type. And if you do want to refer to them by words, you can call them circumstellar or circumbinary. Circum just means around, so around a star or around the binary. There's actually also a less obvious third type of orbit here that is called a T-type orbit. And we'll talk a little bit more about this later, but I'm curious if you can guess what that is just based on the letter T. Also, this is a little bit of an aside because it's not really about stable planetary orbits. This is what we're talking about here. But I read this really interesting paper once about how in evolving star systems, so when these stars are changing mass, you can actually have planets that hop between the stars. They're called star hopping planet orbits, which is just, it's so cool. Okay, so let's start with circumstellar orbits. How extreme can you get? Like, what are the restrictions on having a planet in orbit around one star in the binary? So there are basically 5 major factors which really matter here, and the first 2 are related to the orbit of the binary stars. I should mention here that binary star orbits are maybe a little bit different than what you're picturing when you're thinking of just like a planet orbiting a star or a satellite orbiting the Earth, because in those cases, the thing that is in orbit is so much less massive than the central thing that we kind of just think about it as being in orbit around the first body. But that's actually just an approximation because, of course, they are both in orbit around their common center of mass. But when we're talking about binary star orbits, because the masses are much more comparable, you really can see that they are orbiting the common center of mass. Now, the same orbital concepts apply, but now you can really see that the center of mass is at the focus of the orbit, and they each kind of have their own shape, which has the same eccentricity for both of them. And then you can think of each of these ellipses as having a semi-major axis, but the semi-major axis of the orbit is actually the sum of both of those. But it's the same concept, it just looks a little bit different because it's not operating the same approximation we're used to. Okay, so for a planet around one of the stars, you can probably imagine that how close the other star is really matters, so that would be the semi-major axis of the orbit. The force at play here is gravity, and gravity depends a lot on distance, and so the closer the other star is, the more strongly it can affect a planet's orbit. The other really major factor of the binary star orbit is its eccentricity. And this partly goes back to the distance thing, because the semi-major axis just tells you how far apart they are in general throughout the orbit, but of course, at higher eccentricities, they get closer together at periapsis and farther away at apoapsis, and so the second star is getting a lot closer to the first star at higher eccentricities. For example, stars that are orbiting at a semi-major axis of 1,000 AU in a perfectly circular orbit, they never get closer together than 1,000 AU. But they might get as close together as 10 AU at an eccentricity of, 0.99, which is obviously very extreme. But just to give you an example of this relationship between the distance, the closest distance between the stars and the eccentricity. And aside from just this decreasing periapsis, there's also the fact that when there's more eccentricity in the binary's orbit, there's just kind of more eccentricity at play, and so the planetary orbits can get more eccentric, which can make them less stable. The third factor is the relative masses of the stars. So imagine you have a really uneven mass ratio where one star is much bigger than the other one. You can imagine that a planet that's around the smaller star, one is going to be held less strongly to that star because there's just less gravity from that star to hold on to it. And the other is you're going to get more gravity from the other star because it's more massive, and so you're going to get larger perturbations to the orbit. So being around the less massive star would probably be less stable than being around the more massive star. The last two factors are related to the planetary orbit. So if you're looking at the system edge on, if the planet and the stars are always in the same plane, then they have an inclination of 0. But of course the planetary orbit's inclination can change. It can be anything. So that could be coplanar with an inclination of 0. It could be polar, we have an inclination of 90 degrees. It could be perfectly coplanar retrograde, where we have an inclination of 180 degrees, or really anything in between. And last one is where the planet is orbiting. So you can imagine that a planet orbiting closer to its star is going to be less affected by the other star, whereas a planet that's orbiting farther away is going to be more affected. So the semi-major axis of the planetary orbit matters. Yeah, I guess that is kind of complicated. But the three-body problem always delivers on the fun, doesn't it? Now note that one thing that I didn't mention here is the mass of the planet itself. And that's just because in general, the planet's mass is going to be so much smaller than the mass of the stars that it is pretty negligible. And a lot of times you can actually just consider the planet to have 0 mass, which is just a little bit simpler and can really speed up the computation. So work smarter, not harder. Or you can just consider it to have an arbitrary mass. A lot of times, a Jupiter mass planet is used, but it doesn't really have a strong effect on the outcome. Now we have all of these 5 factors that are going to influence the stability of a circumstellar planet, but working with 5 factors is kind of a lot. So there are ways that we can kind of collapse that down into a smaller set of factors. So for example, a common way to characterize the stability of planetary orbits in a multiple stellar system is something called the critical semi-major axis ratio. So basically this is the most extreme semi-major axis that the planet can have and still be stable relative to the semi-major axis of the binary. So we're getting 2 of those factors combined into here, and it's telling us the limit on stability. Now for a circumstellar planet, because the farther it's getting away from the star, the more it's getting affected by the other star, what we're looking at here is the maximum semi-major axis that a planet can have and still be stable. So this ratio of the axes is generally called alpha, and there you go, we've got 2 of our factors now combined into 1. We can also combine the stellar masses into a single number called mu, and this is also a ratio, and it's the ratio of the mass of the non-host star, so the outer star, compared to the mass of both stars. So basically it's like what percentage of the mass is being held in the outer star and not the star that's hosting the planet. So basically we can understand the stability of planetary orbits in a binary star system by looking at the alpha value associated with different combinations of the eccentricity of the binary, the stellar mass ratio, and the inclination between the orbits. As is usually the case with orbital dynamics, you can make some approximations that would allow you to make predictions about the stability based on just theory. Of course, we can't do it exactly because this is a 3-body problem and it just can't be solved exactly in theory. Now that's definitely very interesting and useful in its own right, but that's not what we're going to be discussing basically in this video. We're just going to look at the results from computer simulations. So this is just a numerical method where you simulate a lot of different systems with different properties, and then you look at the results that you get and you make inferences from that about how these different factors interrelate to give you the stability of the system. And an easy way to visualize these results is something called a stability map. There's a lot of different iterations that this could take, but it's basically the concept is it's just a plot, and you can look at it and it will tell you the stability based on some combination of the parameters on the plot. And it will give you kind of a visualization of how those parameters are affecting the stability of the system. So this stability map is from 1988. It is for a binary system with equal mass stars and a coplanar planetary orbit. So that's a mu of 0.5 and an inclination of 0. This axis on the bottom here is showing the eccentricity of the stellar orbit, and then this y-axis here is showing the critical semi-major axis ratio, that alpha value. And then you can show on the plot whether it is stable or not stable. And then there's also this region here that is called the gray region, and that can sometimes be stable and sometimes not be stable. And the reason that you kind of get this gray region here where there's variability in the outcomes is mostly because of the specific orientation of the planet, or like the position of the planet within its orbit. And that can actually really affect the outcome because, these are chaotic systems. And so sometimes really small changes can matter a lot, especially in this region. And so that's why you have this little gray region where sometimes the outcomes are different depending on the exact parameters that you're using in the simulation. And what the stability map is telling us is that as the eccentricity of the binary increases, this critical alpha decreases, which means that the planet is only stable out to shorter distances away from its star. So there's more instability in the system when the eccentricity of the binary increases, which is what we expected to see. Now I said this was from 1988, and I am not going to mention if I was alive then, but this is not a recent result. And you can imagine the kind of computing power they had available to them, so we should be able to do a lot better nowadays, right? Yeah, baby, of course. So let's take a look at some results from a 2024 study. And I should note that this is a preprint, so it hasn't been peer-reviewed yet. Damn, there was a lot more going on here. Let's break it down. So again, we have the eccentricity of the binary stars, although there's a subtle difference here because this goes up to an eccentricity of 0.8, whereas the 1988 results only went up to an eccentricity of 0.6. It gets a lot harder to simulate things at higher eccentricities because you have to resolve a lot closer interactions. But now we have an axis for the stellar mass ratio, and you can see it goes from 0 to 1. So 0.5 on this would be equal mass stars. Greater than 0.5 means the non-hosting star is the bigger star. Less than 0.5 means the hosting star is the bigger star. And the color here is showing that critical alpha. So that was the y-axis on the previous map. Now it is the color. And then each of these 4 panels has a different inclination associated with it, which is that number in the corner there. So we're going from coplanar of 0 to retrograde coplanar at 180, and then a couple in between. So looking at the stability map, what are some of the things that we can kind of take away from this in understanding? Well, for one thing, we can see that as the mass ratio goes down, the critical alpha goes up. So the planet can be farther away from its host star and still be stable, which makes sense because of what we talked about before. That's kind of what we would expect. That means that the planet is orbiting the more massive star at a lower mass ratio, and so it's just going to be less affected by that other star. And then as the eccentricity of the binary goes up, the critical alpha goes down, which is again what we expected to see. Those stars are getting closer together. There's more potential for forced eccentricity of the planetary orbit, so that all combines to make it less stable. Now, when comparing the different inclinations, we can see that the coplanar case and the 30-degree inclination case aren't very different. But then as you get up to 45 degrees of inclination, the critical alphas generally go down, indicating more instability in the system. And this might not be immediately obvious why that's happening, but basically it's because of something that is called the Kozai-Leadov effect, which I'm not going to get into the details of in this video, but basically it can just really destabilize the system and increase the eccentricity of the planets quite a lot, but it only starts once the inclination gets above a certain threshold. So at 30 degrees inclination, you're just not really getting a lot of Kozai-Leadov, but once you get up to 45, you are. Interestingly, the highest alphas in general, so the most stability, is in the 180-degree inclination case, where that is the coplanar retrograde orbits. So when we say retrograde, that just means that the star is orbiting counterclockwise and the planet is orbiting clockwise, whereas in the prograde case, they're both orbiting counterclockwise. Now the difference here is a little bit subtle, but basically when they're both orbiting in the same direction, as the star and the planet pass one another, their relative velocity is a little bit lower because they're both going in the same direction. And so they spend a little bit more time near one another than in the retrograde case where they're going opposite directions, and so they pass by one another a little bit faster because of a higher relative velocity. And so there's just less time for the gravity of the star to interact with the planet when they're on retrograde orbits, and so that's why they're just a little bit more stable than those prograde orbits. You thought the circumstellar ones were going to be boring, didn't you? But there's a lot of complexity here. Let's take this kind of abstract stability map and transfer it into a physical example where we can kind of get some real numbers to help us understand what this all means. Let's think about our own solar system. So let's say the sun had a twin. How close could that twin orbit and not mess up the planetary orbit? So Neptune has the most distant orbit at 30 AU. So you need to have at least 30 AU for that critical semi-major axis. So because they're twins, they have equal masses, so that's a mu of 0.5. Let's just say eccentricity of 0.4 and just coplanar orbits. So that's around, let's say 0.15 based on that color for the critical semi-major axis ratio. So to keep 30 as the numerator there, that means that the denominator, so the semi-major axis of the binary stars, has to be greater than 200 AU, which is actually shockingly close. That was surprising math. So let's consider a binary system that's kind of based off of Alpha Centauri, but it's only a binary system and not a triple system. So we'll have one M dwarf star that's 0.122 solar masses and one G dwarf star that's 1.08 solar masses. They'll be in orbit at about 8,700 AU with an eccentricity of 0.5. And we're considering planets around the smaller star. Now with those solar masses, we're talking about a mu of 0.899, so combined with our eccentricity of 0.5, that puts us right about here. Ooh, that is not looking good, is it? Because that means for a coplanar planet, alpha can't be any higher than, I mean, it's kind of hard to get an exact reading off a color bar, but it's definitely less than 0.1, so say 0.025. And that sounds bad, because 0.025 is tiny, but we're talking about 0.025 of 8,700 AU, so that's still 217 AU. It's actually totally fine for the M dwarf to have planets in this case. Okay, but that's for a very wide binary. What if we looked at just the close binary stars from Alpha Centauri? So those stars have masses of 1.08 and 0.91 solar masses, and they orbit at 17.5 AU with an eccentricity of 0.52. For planets orbiting star A, that would be a mu of 0.46, so that gives an alpha of around 0.15, which means that the planets could only be orbiting out to about 2.6 AU. And if the planets were around star B, which is the slightly less massive one, now you have a mu of 0.54, so the alpha goes down to around 0.1, so we're talking about planets only out to about 1.7 AU. The spacing of the stars really, really matters. Oh, and if you're used to thinking about planetary orbits, these might sound like kind of high eccentricities to be talking about, but actually stellar binaries do tend to have much higher eccentricities than, say, a planetary orbit, so these are totally reasonable eccentricity values to be considering. Alright, let's get to the fun case. Circumbinary planets. No offense to circumstellar planets. Now, surprisingly, the factors to consider here are actually basically the same as it was for circumstellar planets. Or maybe that's not surprising, because really it's the exact same configuration. It's just now instead of this being the less massive one and this being massive, we've just We've just swapped which one is the massive one and which one is not. But there's still an inner orbit and an outer orbit. It's just now we're interested in the stability of the outer orbit. And one big difference there is that we don't really care anymore about the maximum semi-major axis that the planet can have. Instead, we care about the minimum semi-major axis that it can have. So alpha is still going to be the same thing. It's still the ratio of the semi-major axes, but now we're looking at the minimum semi-major axis for the planet. So how close it can get to the binary stars and still be stable. Remember that stability map we saw from 1988? Let's go back to 1986 and see what that same scientist did for circumbinary planets. Again, we have eccentricity here on the x-axis, which is the eccentricity of the star's orbit. And again, we have the critical alpha here on the y-axis. But remember, now we're considering the minimum semi-major axis, and so that means that a lower alpha is actually more stable than a higher alpha. And these values are going to be greater than 1 instead of less than 1. And we actually see the same thing that we saw with circumstellar planets, where the increasing eccentricity of the binary leads to a higher alpha, which is more instability. So less stable planetary systems as the eccentricity of the binary increases. And again, this makes sense. It's what we would expect, because not only does a higher eccentricity for the stars mean that they get closer together at periapsis, which is what we were concerned about before, it means they also get farther apart at apoapsis, which means that the star is getting closer to that planet that is orbiting on the outside. And so again, the star and the planet are going to get closer together at higher eccentricities, so there's going to be a larger effect between the two. And again, also not going to get into the details, but there are concerns with eccentricity resonances and force eccentricity that also contribute to this. One thing that's interesting to compare between these maps is that just looking at zero eccentricity, for the circumstellar planet, the alpha is around 0.25, which means that the outer orbit has to be 4 times bigger than the inner orbit in order for the planet to be stable. But for the circumbinary planet at zero eccentricity, the alpha is 2.4, so the outer orbit only has to be 2.4 bigger times than the inner orbit. So they're not exactly, symmetric scenarios. Okay, let's fast forward a few decades and go back to that same 2024 study and look at their stability map for circumbinary planets. Now this is the same setup where there's the mass ratio along the x-axis, the eccentricity along the y-axis, and the color is the alpha. One thing to note though is that instead of going from 0 to 1 for the mass ratio, it only goes from 0 to 0.5. And that is because since the planet is orbiting both stars, it doesn't really matter which star is the more massive star, it just matters what their mass ratio is. Now conceptually, if you think about kind of the most extreme case here where the mass ratio is almost 0, that means that one of the stars is containing basically all of the mass and the other star is really, really small. And you've basically just recreated a planetary system at that point where you have one primary body, a really small body, and then you now just have another planet external to that. And so that should be really stable. And if you look at the alpha value here in that case, it's like 1.25. So that tracks. That's really close. And that's true even as you increase the eccentricity, you're not getting that much instability. It's mostly just if you start to get into orbit crossing. In general, as that mass ratio increases, the dynamics between the stars start to become really important. The planet has to move further out, alpha increases, less stable, all that jazz. But interestingly, that's not the case at every eccentricity. For example, looking at an eccentricity of 0.6, you can see the critical alpha starts at around 2.75, and then as the mass ratio increases, that alpha increases up to a max of around 4 at a mu of 0.45. But then as the mass ratio increases even more towards equal mass stars, the alpha actually goes back down to around 3.5. And that means that the most unstable systems, the highest critical alphas, are actually not at the highest mass ratio and highest eccentricity, which is what you might expect based on their individual trends. It's actually at the really high eccentricities, but at a mu of around 0.2. This was actually really surprising to me, and I had to do some digging because they didn't really talk about it in the paper. But I think what is happening here is that the maximum possible eccentricity that the planet can get forced to is proportional to this cubic relation with the mass ratio. And that relationship peaks at around 0.2. And the higher the eccentricity of the binary, the more eccentricity is kind of available to be forced into the planetary orbit. And so you get the highest planetary eccentricities at this particular peak. And of course, more eccentricity of the planet, it means more instability and the planet has to be farther up. Okay, but this map is just for coplanar systems. So what happens when we add a good old dose of inclination into the mix? Well, here's another 2024 study that looked at fully 3D configurations. So they also found that the eccentricity of the binary had the largest effect on the stability of the planet, and then the mass ratio of the binary had a significant but less strong effect. And then they found that the mutual inclination had an effect that was around the same strength as the mass ratio. So the mass ratio and the mutual inclination are equally important, and the eccentricity is even more important. They found that retrograde circumbinary planetary orbits are a little bit more stable than coplanar ones, which again, we saw that with circumstellar planets as well, so that's not surprising. Although it did turn out that it wasn't 100% of the time more stable, because orbital dynamics can just never be that predictable, I guess. These plots show how the mutual inclination affects the stability of planetary orbits in, various configurations, and they're actually showing results from multiple studies in these plots, which is really great because you can compare, multiple results at the same time. In general, you can see that the critical alpha decreases, that is, gets more stable as the inclination approaches 180 degrees, where of course 180 degrees is that coplanar retrograde configuration. And although it's not exactly the same, we do see kind of some version of this trend for all of the configurations here, and some of them show kind of an increase in instability, so higher alphas, right at that 90 degrees, which would be a polar orbit, where the planet is kind of orbiting exactly perpendicular to the stellar orbits. To be honest, this was a bit of a surprise to me. I actually thought that the mutual inclination was going to have a lot bigger effect here, but that's just how it was. Okay, so that's circumstellar and circumbinary planets, that is S-type and P-type. But I mentioned before that there's actually a third type as well. Now it's a little bit less easy to explain than just orbiting one of the stars or orbiting both of the stars. So these are called T-type orbits, and the T here is for Trojan. So some of you might see where I'm going with this. Just like the Trojan asteroids share Jupiter's orbit near the L4 and L5 Lagrange points, you can have this same configuration, but instead of star-planet-asteroid, you have star-star-planet. Now, just like the sun is a lot more massive than Jupiter, you have to have a really large disparity in the masses of the stars in order for this to be possible. But stars come in a huge range of masses, from like 0.1 solar mass all the way up to 100 or more solar masses. So this isn't an impossible scenario, and if you had this, that would be a T-type planet. And I'm really curious, did any of you actually guess what a T-type planet was just from the name T-type? If so, major props, because I would never be able to do that. Okay, so we've talked about planetary orbits in binary systems, but can we get crazier? Can we go to trinary systems or even more? Well, now we've made our 3-body problem into a 4+ body problem. So before we can even add in that 4th body, the planet, we have to know if the 3-body part, the stellar system, is even stable. And basically, that just comes down to whether the stellar system is hierarchical, which is incidentally a very fun word to say. In a hierarchical system, you have a very clear separation or hierarchy of scales. So for example, if you have 2 stars that are kind of, in orbit with one another at some distance, if they're in orbit with a 3rd star, if that star is really far away, then you can kind of consider these 2 stars as being like a single object in orbit with this object, and that's going to be stable because that's hierarchical. But if you have very similar distances between all 3 stars, no, not stable. And you don't just have to stick with 3 stars, you can extend this up to really any arbitrarily high number of stars, and the highest multiplicities that we actually know of are actually 2 septenary systems, and if you're up on your Latin, you know that means 7 stars in the system. But let's just stick to trinary. So assuming you're starting from a stable triple star system, the considerations for a circumstellar planet and its stability are mostly the same as if it was just a binary. So think about this. You basically have 2 configurations where you could have a circumstellar planet. It could be either orbiting one of these stars in the close binary, or it could be orbiting the star that is, widely separated from the other 2. If it's orbiting one of the close stars, then the other star in the close binary is going to be way more important than this star way over here. And so you can kind of just consider this as if it was its own binary system and ignore the 3rd star entirely. On the other hand, if it's orbiting this wide star, well then these stars are really far away. You can kind of just consider them as one body. And so again, you've just recreated a binary system with a circumstellar planet. And so it's the same sort of considerations that you're looking at there. But mostly the same is not exactly the same. And so actually this 2018 study found that for a circumstellar planet in the close binary portion of a trinary system, the critical semi-major axis shrinks by about 30%. So there definitely is a little bit more restriction because of this stellar companion over here. Whereas for circumstellar planets orbiting the single star, not near the binary, it's actually only a difference of about 5%, so even less. So not that big of a difference, but a little bit. Okay, so now for circumbinary planets. Now there's only one way you can have circumbinary planets in a triple star system, and that is orbiting the 2 close binary stars. And the biggest effect here comes from this outer star. So that is, if you were to transform this triple star system into a binary system, removing this outer star and just considering a circumbinary around, an equivalent binary system would be more different than if these 2 binary stars were like a single star of the same mass, and then you just had a circumstellar orbit. And the biggest factor from this outer star probably isn't a surprise to you because it's been the biggest factor this whole time, and that is the eccentricity of the orbit of that star with the binary stars. So now you have two different stellar orbits to consider here, right? You have the binary, the close binary orbit, and you have the wide binary orbit. So the eccentricity of the wide binary orbit has a really big effect on the planet orbiting the close binary. And of course, it's the same trend. Eccentricity going up leads to more instability of the planets. And it turns out that even high mutual inclinations of this outer star actually doesn't have that much effect on the stability of the circumbinary planet, which was, again, a surprise to me because inclination can really fuck things up, but I guess in this case it's just not. And once again, we do see here that the retrograde orbit of the outer star is a little bit more stable than having a prograde orbit. Okay, but I'm sure what you really want to know about a triple star system is, are circumtrinary planets possible? And the answer is yes. Basically, this is just a little bit more complicated version of the circumbinary orbit. So again, now instead of just having one stellar orbit, you have two stellar orbits. And again, the eccentricity of that wide second orbit is the one thing that has the biggest change from just a circumbinary scenario. So we can look at the same figure we saw before, but now for a circumtrinary planet. And we see, again, of course, increasing the eccentricity leads to more instability and a higher critical alpha, because again, we're looking at the minimum semi-major axis that circumtrinary planet could have. And we can also see here now that the mutual inclination has a lot more effect for a circumtrinary planet than it does for a circumbinary planet in a triple system. And there are different combinations here, so you can have, prograde star, prograde planet, or retrograde star, retrograde planet, or of course mix and match. So the most stable scenario is retrograde star, prograde planet, and the least stable is prograde star and prograde planet. And so then this tells us that the mutual inclination of that third star actually does matter. So we can go ahead and look at how alpha changes based on what that mutual inclination is. And we can see here that there is a large effect, especially for retrograde stellar orbits, which are shown here in black. So you can see that with retrograde coplanar, the planet can be a lot closer. But as that mutual inclination increases, the planet starts to get farther and farther away. And this is actually primarily due to, again, that Kozai-Lito effect. And you see this kind of stair-step, stripy distribution going on here that's usually pointing to some sort of resonance where things are getting kind of forced into these discrete configurations, which is just fascinating. This whole paper was fascinating. I'd never read it before I started to make this video, and it was such a fun read. I learned so much. Okay, so now we know that all sorts of interesting planetary orbits are possible in multiple star systems. That is, they would be stable and they could exist. But could you actually form planets in these kind of orbits in the first place? Now, diving into all the theory to answer this question is a whole nother video, but we can empirically answer this question to a certain extent, because if we know that exoplanets exist in these configurations, then obviously it must be possible to form them in these configurations. Now, we've already mentioned that Proxima Centauri has circumstellar planets in a triple star system, so we know that it must be possible to form circumstellar planets. And in fact, we know of 944 circumstellar planets in 717 different stellar systems, so definitely possible. All right, here's the big one that I promised to answer for you at the beginning of the video. Is Tatooine possible? Can you form circumbinary planets? And the answer is yes. That's right, we know of actual, real circumbinary planets that exist in 30 different stellar systems. We actually know of 38 circumbinary planets. Now, we already know that circumstellar planets are possible in triple systems because of Proxima Centauri. And in fact, these are the most common types of circumstellar planets to be found in triple systems. But we do actually know of exoplanets that are orbiting one of these stars of the close binary portion of a triple star system, like KOI 5AB. Now, to my knowledge, there are no confirmed circumbinary exoplanets in triple star systems, but there is a circumbinary planet in a quadruple star system, Kepler 64b. So yes, this is possible. And also, how cool is this? This exoplanet was actually the first planet discovered in a quadruple star system at all, and it was discovered by citizen scientists, which I love to see it. And dare we ask, are there any known circumtrinary planets? Okay, sorry, the answer to this one is no, there are no known circumtrinary planets. However, there is a known circumtrinary protoplanetary disk, and planets form in protoplanetary disks. So this is a very good sign that there could, in fact, possibly be circumtrinary planets, and hopefully we will find one someday. Now, the fact that we know of these kinds of planets means that they can and do exist, which is really exciting. But it doesn't actually tell us very much about how common these kinds of planets are, and that is just because detecting planets in multiple star systems is way harder than detecting them around single stars, and so we just don't have that kind of information yet. Oh, there is just so much more we could talk about when it comes to planets in multiple star systems, like their formation, habitability, seasons, day-night cycles, so let me know if you're interested in that. But this has been quite enough for one day, so we'll live again to talk more astrophysics soon. Bye!